Most of us carry a simple assumption about the future in space. When humans finally leave Earth for good, we will go to Mars first. Mars has been framed as the obvious next home for a long time, a place with days and seasons, a thin atmosphere, and the promise, at least in our imaginations, of becoming something like a second Earth. The Moon, by contrast, is usually filed away as a stopover, a destination for flags and footprints, for science outposts, for temporary bases that feel more like camps than cities. It is emotionally familiar, hanging there in the sky, close enough to feel almost harmless. And yet, when you look at it scientifically, it seems limited. No breathable air, no open water, 2 weeks of daylight followed by 2 weeks of night, and a surface exposed to radiation and micrometeorites. Mars feels visionary, like a bold leap into the unknown. The Moon feels like the porch, close, useful, but not where a civilization begins. And yet, modern spaceflight planning has a way of quietly challenging our everyday assumptions. Not with sudden announcements that change everything overnight, but with small shifts in priority, the kind that only become obvious after you notice where the money, the engineering time, and the launches are actually going. In recent years, SpaceX has appeared to tilt its center of gravity, not away from Mars entirely, but toward the Moon as the nearer, more immediate proving ground. Then, on February 8, 2026, Elon Musk stated that a self-sustaining lunar city may be achievable in under 10 years, while a self-sustaining city on Mars may take more than 20. Those are just numbers in a sentence, but they force a quiet reconsideration. If the Moon could host a permanent city first, then humanity's expansion into space might begin in a different order than the story we have repeated for decades. And that leads to the unsettling question at the center of tonight's journey. Could the first true human city beyond Earth be built not on Mars, but on the Moon? Not a research station that depends on constant resupply, not a short expedition, a city with enough industry, energy, and life support to keep going, even when Earth cannot help. It is a practical question, an engineering question, a logistics question, and still, it carries a faint, eerie weight, because a city is not just metal and machines. A city is time. A city implies birthdays and routines and long-term plans, played out under a sky that does not behave like Earth's. Tonight, we will move slowly through the pieces of this idea. We will talk about Starship, and why its real power is not only its size, but the concept of orbital refueling, a method that could turn single launches into repeating supply lines. We will look toward the lunar South Pole, where the sunlight angle is strange, and where places like Shackleton Crater may hide water ice in permanent shadow. We will consider a simple, slightly uncanny possibility that the first habitats might not be elegant domes, but landed starships themselves, converted into living and working spaces after touchdown. We will explore how people might protect themselves, not with thick glass, but by burying structures under regolith, the Moon's fine, abrasive soil, using the ground itself as shielding from radiation and tiny impacts. We will talk about water ice, not only for drinking and air, but as a feedstock for fuel production, so the Moon becomes a place that can launch ships, not just receive them. And we will keep Mars in view the whole time, because the Moon may not replace the Martian dream. It may become the stepping stone that makes it possible. Along the way, we will also touch the quieter machinery behind all of this, the role of artificial intelligence and autonomy, because a lunar city, especially in its early years, would depend on systems that can operate for long periods with minimal human attention. Robots that build, software that schedules power and oxygen, and machines that keep working through the long lunar night, or through regions where the sun barely rises. If you enjoy thoughtful late-night science explorations like this, you can gently support the channel by liking the video and subscribing to the Sleepy Cosmos channel for more quiet journeys through space, physics, and the future of civilization. And now, let the strange part settle in. If a permanent off-world civilization begins on the Moon, it begins only a few days away by spacecraft, not months away across interplanetary space. The first true human city beyond Earth might start, not in a far rust-colored wilderness, but on the pale surface we once treated as temporary. But to understand why the Moon now seems more practical than Mars, we first need to understand what changed in SpaceX's thinking. For many years, the moon was spoken of as a kind of side quest, a detour, a distraction from the real destination, Mars. Elon Musk said this in different ways across different interviews, that going back to the moon did not really build a city, that it was too close, too familiar, that it did not force the same level of invention. And it mattered, because SpaceX built its public identity around a single sharp story: reusable rockets, lower launch costs, a spacecraft called Starship, and a future where the first self-sustaining settlement would rise under a salmon-colored sky. So when that story began to bend, when the moon started being described not as a distraction, but as a first step, it sounded at first like a reversal, almost like a contradiction you could hold in your hand. The company most associated with Mars, now leaning into lunar landings, lunar cargo, even the suggestion of a lunar city. But if you watch the logic carefully, the change can be calmer than it seems. Not an abandonment of Mars, more like a practical recalculation under a new set of constraints. Because building a civilization is not only about where you want to go, it is about how often you can try, how fast you can recover from mistakes, and what happens if Earth stops answering. That last detail tends to sit quietly in the background, but it changes almost everything. Musk has spoken, more than once, about a fear that a distant colony could simply die, not from a single dramatic failure, but from a slow starvation of parts, tools, and support. If Earth had a catastrophe, something natural like a global pandemic or a chain of crop failures, something man-made like a major war, or even something technical like a severe economic collapse that pauses launches for years, a young Mars settlement would be fragile, and fragility is not always obvious at first. You can have a greenhouse, you can have oxygen production, you can recycle water, but then a valve fails, or a seal degrades, or a pump needs a replacement bearing, and the replacement bearing is on Earth. On Mars, you cannot just wait a few weeks for the next cargo ship. Even in the best case, you wait many months, and in a worse case, you wait until the next time Earth and Mars line up properly. So the unsettling thought is not that Mars is impossible, it is that Mars is unforgiving, in a way that punishes interruptions. A settlement can be technically impressive and still not be self-sustaining. And if it is not self-sustaining, it is not yet a branch of civilization. It is a remote facility with a long umbilical cord. This is the resupply problem. In its simplest form, a colony that needs help is a colony that can be cut off. Now, bring the same problem closer. The moon is only a few days away by spacecraft. That sounds like a convenience, but it is more than convenience. It changes the risk model. If a lunar outpost discovers a design flaw in its life support, if dust is destroying seals faster than expected, if a power system performs poorly in the real environment, you can respond quickly. You can send spare parts. You can send an upgraded system. You can send a new team. If you must, you can bring people home. Recovery and adaptation become possible at human speed, and redundancy becomes more realistic, not because the moon is gentle, it is not, but because you can afford to build layers of backup, multiple landers, extra tanks, extra habitats, duplicate power systems. You can iterate, the way engineering actually progresses, through repeated contact with reality. Mars makes iteration slow, and therefore expensive, and therefore rare. And this leads into a second constraint, one that is quiet, mathematical, and brutal. Mars launch windows. To reach Mars efficiently, Earth and Mars need to be in the right alignment. This happens roughly every 26 months. A little over 2 years. That means if you launch a mission, and something goes wrong, a small error, a misjudged requirement, an unexpected failure mode, you may not get another chance to try again for more than 2 years. 2 years is a long time for a new technology. 2 years is a long time for a new settlement design. 2 years is a long time for a crew living with the consequences of early decisions. Even if your spacecraft can technically launch at other times, the fuel cost becomes punishing. And a civilization does not grow on punishing margins. A civilization grows on repeating routes, predictable schedules, and the ability to improve rapidly. This is where the moon becomes almost uncomfortably attractive, because it is always there, always nearby. You can launch to the moon far more often. You can test landing systems, test surface operations, test power storage, test construction robots, test closed-loop life support. And if the test fails, you do not lose 2 years. You learn, you adjust, you fly again. Operational learning becomes fast, not fast in a dramatic way, fast in the way that factories improve, one revision, then another, until the system stops being an experiment and becomes infrastructure. So the moon first idea can be read as a kind of engineering honesty, a recognition that the hard part is not reaching a world, it is creating a repeating process that keeps working. And beneath this, there is a deeper motive that Musk sometimes describes in philosophical terms, a phrase that can sound strange in a business context, the survival of consciousness. The idea is, humanity is not just a species, it is a carrier of experience, a way for the universe to look back at itself in a small, local way. And if Earth suffers a catastrophe, then the story could narrow or end. Now, this is not a scientific statement in the strict sense. Physics does not require consciousness to persist. The cosmos would continue either way, but as a guiding value, it changes the architecture of the plan. If the true goal is to protect the long-term continuity of human life and culture, then the first priority is not romance, it is resilience. You want an off-world branch that can survive, even if Earth has a bad century. And a nearby lunar city is a plausible first branch, because you can build it up gradually. You can keep it supplied while it learns to supply itself. You can add capability in layers. Early habitats, then better power, then water extraction, then metals processing, then manufacturing, then the ability to repair its own machines, then the ability to expand without waiting for Earth's next shipment. In this frame, the moon is not the final refuge, it is the first stable foothold, where the techniques of permanence are practiced. And there is another part of the logic, less poetic, more industrial. What if the moon is not only a place to live, but a place to make things? There have been suggestions, from Musk and from many space industry thinkers, that a mature lunar presence could support industrial production, especially for orbital infrastructure. Orbiting platforms, large space telescopes, fuel depots, radiation-shielded habitats in space, structures that are awkward to launch fully built from Earth, because Earth's gravity is expensive. If you can produce some materials off Earth, even simple things like oxygen, water, certain metals, or construction feedstock, then space starts to change from a place you visit to a place where you can build. And in a world increasingly shaped by computation, there is also a speculative but practical-sounding thought that future industry may hunger for energy and cooling, for data centers, for large-scale computing, for artificial intelligence training and operation at massive power levels. The moon is harsh, but it is also a platform, a place with vacuum, extreme cold in shadowed regions, long sunlight near certain poles, and wide-open terrain for power generation. None of this is guaranteed. It is not established that the moon will become an industrial hub, or that lunar manufacturing will beat Earth-based manufacturing in cost. But it is a serious direction of thought, because it treats the moon not as a flag-planting destination, not as a museum of footprints, but as a node in a growing system, a system that could, in time, feed itself and produce more capability than was initially shipped from Earth. That difference matters. An outpost is static, a city is dynamic. A city does not merely survive, it metabolizes, it repairs, it grows. And this brings us back to Mars, because moon first does not have to mean Mars never. Musk's framing, at different times, has been that Mars remains the long-term goal, but that the moon can be the nearer proving ground, a place where Starship operations mature, where orbital refueling becomes routine, where high-cadence launches and landings become normal, where life support becomes robust through repetition, where surface construction becomes something you can do without improvising every step. In that architecture, Mars becomes the deeper frontier, the place that still demands more. Long travel times, harsher resupply constraints, a different kind of environmental challenge. But the moon becomes the faster classroom, the place where you make your mistakes while help is close, and where you build up the industrial and operational muscle that a real Martian settlement would eventually need. So the pivot is striking, yes, especially given how strongly SpaceX has been tied to Mars in the public imagination. But it can also be read as a cold, logistical insight that the first off-world civilization will probably not begin where the dream is most dramatic. It will begin where learning is fastest, where failure is survivable, and where supply lines are short enough that you can afford to keep trying. Yet even if the moon is the better first step, that still leaves a deeper question. What kind of physical base could actually become the seed of a lunar city? To build anything that deserves the name city, you need more than travel. You need foundations, you need routines, and you need a way to keep your machines alive in a place that wants to break them. So the moon-first pivot, if we take it seriously, becomes a question of strategy, not just of destination. A nearby world lets you practice the ordinary work of survival: shipping schedules, maintenance cycles, training crews, replacing parts before they fail, and learning what breaks, not in theory, but in the dust, and cold, and radiation. In that sense, the reversal is less like changing the dream, and more like changing the order of operations. Mars can still be the long horizon, but the moon becomes the workshop, a place where you can turn a spacecraft into a transport system, and turn a habitat into a neighborhood, one repetition at a time. This is one reason the moon keeps reappearing in serious space plans, even among people who do not especially love it. Because distance is not only a number, distance is a form of pressure. It presses on every decision: how much you pack, how many spares you fly, how much risk you accept, how quickly you can correct the errors you did not know you were making. On the moon, if you discover your dust filters clog in half the expected time, you can redesign and fly the improved filter soon. If a certain seal compound becomes brittle, if a suit joint wears down too quickly, if a habitat wall needs more shielding than you calculated, you can learn it, fix it, and send the fix without waiting through years of silence. And this practicality has a psychological side that is easy to overlook. If you are trying to create a self-sustaining settlement, you do not want the first time you face a rare failure mode to be when you are many months away, with no rescue and no replacement parts. In an environment where small problems can become quietly terminal, a nearby settlement is not safe, but it is more recoverable. And recoverability is one of the hidden ingredients of resilience. There is also a subtler implication in this moon-first logic: the idea that the first true off-world branch of civilization may not be defined by a single dramatic leap, but by a gradual thickening of capability. More power than you need, more water than you planned for, more storage, more redundancy, the slow accumulation of margins. Margins are not inspiring, but margins keep you alive. When Musk talks about a city, he is not usually describing a few buildings placed on the surface like props. He is talking about something that can keep functioning through interruptions, through supply delays, through political shifts on Earth, through economic downturns, through the strange periods in history where attention and funding evaporate. A Mars settlement, early on, could be astonishing and still be dependent. A lunar settlement, built the right way, could become boringly reliable, and that is almost the point. Reliable systems are the ones that can be scaled, and scaled systems are the ones that can turn into an enduring pattern. If the philosophical goal is continuity, a lasting thread of human life beyond Earth, then you want your first thread to be thick, not heroic, thick. And the moon offers a place to thicken that thread with repeated launches, repeated deliveries, repeated construction, until the settlement is not just surviving, but reproducing its own capabilities. And that brings back the industrial idea, not as a side project, but as a requirement. Because a city that cannot make, cannot truly endure. It can only receive. The lunar surface is covered in regolith, fine broken rock, not useful by itself, but potentially a feedstock. The poles may hold water ice in permanently shadowed regions, not guaranteed in every spot, and not easy to extract, but important enough to change the map of human plans. Water is not only for drinking, it is also for oxygen, and it can become rocket propellant. Which means, in principle, the moon can become a refueling and construction node, a place that helps build the rest of the infrastructure of space. This is not settled science. It is not a promise. It is an engineering bet that the moon's resources and its proximity allow an economy of repetition, and that repetition can grow into industry. A self-growing civilization is not an outpost with better branding. It is an organism. It uses energy. It processes raw material. It repairs damage. It builds new tools, and it expands its range. That is the deeper logic behind the moon-first execution. It is an attempt to move from expeditions to metabolism, and still, Mars remains in the background like a colder star, not cancelled, not replaced, but postponed into parallel development, a frontier that will demand the mature version of every system. So the Moon becomes a proving ground, a place where Starship or any large transport system can become routine, where orbital refueling can be practiced until it is dull, where habitats become standardized, where surface logistics become a discipline, not an improvisation. Then, when you finally face the long Mars windows, you do it with tools that have already lived through years of real use, not just tests. Yet, even if the Moon is the better first step, that still leaves a deeper question. What kind of physical base could actually become the seed of a lunar city? One answer is almost embarrassingly direct. If you can land a very large spacecraft on the Moon, and it is already pressurized capable, and it already contains tanks, plumbing, power systems, thermal control, avionics, then the simplest first building may be the spacecraft itself. Not as a visitor, but as a resident. A Starship that does not return home is a different kind of object. It stops being a vehicle you use up and becomes infrastructure you deliver. That shift sounds small, but it changes the economics and the engineering at the same time. Because the hardest part of building on the Moon is not designing a room. It is delivering mass, delivering volume, delivering sealed pressure vessels, and delivering all the complex, failure-prone machinery that keeps humans alive. If a single landing can deliver something that is already a sealed metal mountain, then the base begins, the instant the engines shut down. This idea is not new. Space history has an old habit of turning leftover hardware into living space. Skylab, for example, grew out of rocket technology. A large stage reworked into a station, a pressure vessel that was never meant to be a home in the ordinary sense, but became one. There were earlier proposals too, wet workshop ideas where an emptied rocket tank would be outfitted after launch. These concepts always carried a strange logic, not building a habitat and then launching it, but launching something huge and then admitting, quietly, that you can live inside it. A lunar Starship habitat would be that same logic, carried to a larger scale and placed on a surface where volume is precious. The spacecraft becomes delivered infrastructure, a prefabricated shell, a bundle of systems, and, most importantly, a vast interior void waiting to be civilized. And Starship, at least on paper, is a particularly good candidate for this. Most lunar landers in history were designed to be as small as possible. They were careful, minimal, almost cramped on purpose, because every kilogram was painful. Starship's design philosophy is different. It is built around the assumption that mass to orbit becomes cheap enough that you stop shaving every corner and instead build something large, reusable, and tolerant of extra capacity. That large part matters, because in space architecture, empty volume is not a luxury, it is a form of safety. It is room for redundancy, room for storage, room to isolate problems, room to separate noisy machinery from sleep, room to add capabilities later without rebuilding from scratch. Some analyses have claimed that if you repurpose the interior volume effectively, the habitable space could be around 2.5 times the International Space Station. That number depends on how you count, and on how much of the structure you can truly convert. But the underlying point remains. Starship is unusually big. Big enough that you can imagine, not just a few bunks, but labs with real bench space, a medical corner, exercise equipment that is not folded into a closet, workstations for surface operations, storage rooms, spare parts, food reserves, a place to take off a dusty suit without dragging the Moon through your habitat, and still have corridors wide enough to move through calmly, even when everyone is tired. In a small lander, every task becomes a choreography. In a larger volume, the choreography relaxes. And relaxed choreography is one of the quiet foundations of long missions. Now, there is a reason this concept keeps returning. It does not require a miracle redesign. The near-term vision often described by proponents assumes minimal changes to something close to the current human landing Starship concept. The version designed to go from lunar orbit to the surface and back. In other words, you do not wait for a perfect, bespoke moon base module. With custom walls and custom layouts and a custom launch vehicle, you land what you already planned to land, and then you treat it as the first building. The proposal leans on features that are already supposed to exist: airlocks, hatches, ports meant for refueling, interfaces for power and fluids. Rather than slicing the ship into a completely new architecture, you use what is there, and you add internal structure gradually. This minimal changes, maximum utility approach is not as romantic as a gleaming lunar dome, but it is closer to how engineering survives contact with schedules. Staying close to current hardware improves realism, because every added novelty adds new testing, new failure modes, new reasons for delays. A plan that can begin with the vehicle you already need has a calmer path to being attempted. Still, there is an immediate awkwardness. A Starship on the moon lands vertically. It stands tall, like a tower. That is a dramatic image, and also a slightly inconvenient one. If your door is many meters above the ground, every exit becomes a ladder problem. Every cargo transfer becomes a crane problem. And inside, a tall cylinder is not automatically comfortable. On Earth, gravity makes up and down obvious, and multi-floor buildings feel normal. On the moon, gravity is weaker, but it is not absent. You still have a down. You still fall. And if you build your base like a vertical silo, you may discover that daily life becomes a continuous sequence of climbs. So there is a curious, almost unsettling idea that appears in some planning discussions. Land the Starship upright, then tip it onto its side, slowly, deliberately, using robotic rovers, winches, or purpose-built surface equipment. Not a crash, not a tumble, but a controlled lowering until the vehicle rests horizontally. Why do that? Because a horizontal orientation behaves more like a conventional building. You can place entrances near the ground. You can connect tunnels and adjacent modules more easily. You can align sleeping areas, labs, storage, and airlocks along a single axis, like rooms in a long research station. You can build up a base layout that expands outward instead of upward. And psychologically, horizons matter. A habitat that stretches along the surface can feel less like living inside a chimney. Of course, tipping a spacecraft is not trivial. It asks uncomfortable questions, the kind engineers like to postpone and then cannot. Is the structure strong enough, not just to handle launch loads and engine thrust, but to handle side loads during a controlled tip? What happens where the hull meets the regolith, that fine broken lunar rock that behaves partly like dust and partly like soil? Will it support the vehicle, or will it settle unevenly, creating stress points? In low lunar gravity, weight is reduced, which helps, but inertia still exists. If you start a rotation, you must control it. The plan implicitly assumes careful preparation of the ground, perhaps compacting regolith, perhaps using berms, perhaps placing supports, perhaps even partially burying the hull once it is down. It is a concept that could be made to work, but it would demand a kind of surface construction capability early, robots that can dig, push, anchor, and measure, with patience. Patience is often the hidden requirement of space building, and the moon does not reward haste. Now, whether Starship stays vertical or becomes horizontal, the deeper promise is the same. Inside that stainless steel skin, there are large tanks that once held propellant, that were designed to be sealed, strong, and lightweight. If the mission is a one-way delivery and those tanks are empty, then their volume becomes an invitation. The idea is to convert tank volume into pressurized human space. Again, this has echoes of the old wet workshop concept, but now applied at a lunar scale, with modern robotics, modern materials, and, ideally, a steady cadence of resupply. In practice, converting tanks into habitat is not as simple as opening a door. Tank interiors were not designed for human comfort. They are not naturally subdivided. They do not have floors. They may have internal structures, baffles, reinforcements, plumbing. They will need cleaning, inspection, and probably surface treatment to make them compatible with long-term life support. But the basic engineering path is imaginable. You install floors, not just one, but multiple levels. You add partitions to separate noisy equipment from quiet sleep areas, to provide privacy, to create air handling zones, to isolate a fire if the worst happens. You route cables, data lines, power distribution. You add water systems, not only for drinking and hygiene, but for thermal management, because heat disposal in vacuum is a constant design constraint. You install lighting, carefully, thoughtfully, because the human nervous system does not accept darkness for months without consequences. And gradually, furniture appears. Not decorative furniture, but practical pieces, restraint points, handholds, work tables, stowage racks. Over time, the ship becomes multi-level, not a shell you camp inside, but a layered interior, where different functions can be separated and optimized. A place with a rhythm. A place where someone can do paperwork, while someone else repairs a valve, while someone else sleeps, without the entire habitat becoming one shared breath. This gradual conversion is important, because it matches how real outposts tend to grow. You do not arrive to perfection. You arrive to a minimum safe environment, and then you keep improving it. And a large vehicle provides something that small habitats struggle to offer: the ability to improve without constantly tearing down what already works. There is another dimension here, one that sounds less like engineering and more like policy. If Starship becomes a big, usable, pressurized volume on the moon, then it becomes real estate. And real estate has a strange power to turn a fragile political project into an economic one. A single nation might fund an outpost and then lose interest. A single program might change leadership and then change priorities. But a habitat with abundant internal volume can be shared, leased, portioned. You could imagine sections rented to other nations, to universities and research groups, to private companies that want a laboratory in lunar gravity, or a place to test hardware in harsh radiation and dust, or to conduct astronomy with long nights and stable ground. Leasing internal space creates recurring revenue, a steady stream that helps pay for maintenance flights, spare parts, surface power upgrades, and the slow, unglamorous work of keeping the base safe. This is not guaranteed, and it may not even be the initial motivation, but it addresses a central problem of off-world settlements: financial durability. A presence that depends entirely on annual political attention can be strangely brittle. It can feel ominously temporary. A presence that has multiple stakeholders, multiple users, multiple customers can become harder to abandon. Not impossible to abandon, but harder. The base becomes not only a symbol, but a service, and services, if they are useful, have a way of persisting. So the core idea here is almost minimalist. Do not wait for a perfect moon city. Deliver a very large spacecraft, and let it become the first building. Use it as habitat, as lab, as warehouse, as machine room, as a staging point for everything that follows. A ship that stops being a ship and becomes a piece of the landscape. And yet, there is a quiet catch. A repurposed Starship is only useful if it lands in the right place. And on the moon, location may determine whether a settlement thrives or fails. Because on the moon, there are no neutral locations. There are places where the sunlight behaves politely, and places where it vanishes for 2 weeks at a time. There are ridges that stay warm enough for machinery to survive, and bowls that become cryogenic traps. There are regions where the ground is relatively firm, and regions where it may be a deep, powdery layer that has never been disturbed, waiting to swallow wheels, and patience. When you turn a spacecraft into a building, you inherit a new kind of engineering. Not ascent trajectories, not docking targets, but geology and seasons and long-term logistics. A habitat is not just a pressure vessel. It is a negotiation with its environment. And the moon, despite looking quiet, can be strangely unforgiving. If Starship is meant to become a long-term home, then the landing site must support more than a landing. It must support a supply chain. You need a place where cargo can be moved without constant risk, a place where dust does not immediately bury mechanisms, a place where you can build pathways and eventually connect other modules, power lines, communications, radiators, maybe even protective berms. And then there is power, always power. A large habitat is a hungry thing. It needs electricity for air circulation, for carbon dioxide removal, for pumps, computers, lights, and for the quiet, steady warming that keeps systems from freezing. If your location forces you to rely on batteries through long lunar nights, your base becomes less like a settlement and more like an extended camping trip with fragile equipment. So many proposals drift naturally toward the lunar poles, especially the rim regions near permanently shadowed craters. Not because they are comfortable, they are not, but because the poles offer two rare gifts in the same neighborhood. The first gift is the possibility of near-continuous sunlight on certain high points. Not constant, not perfect, but better than most places on the moon. The second gift is the eerie one. In some permanently shadowed regions, The temperatures are so low, and have been so low for so long, that water ice may have survived for billions of years. Not liquid water, but frozen grains mixed into the soil. If that ice can be reached and extracted and purified, it becomes more than drinking water. It becomes oxygen for breathing, and hydrogen and oxygen that can be turned into rocket propellant. And suddenly the choice of landing site is not only about comfort, it is about whether the moon can help feed the settlement. This is where the calm logic of repurposing Starship becomes tightly connected to the landscape. A one-way Starship habitat is a very large, very capable first room. But the moment it is on the surface, it becomes fixed. It is hard to relocate. You cannot simply pick it up and try again somewhere else. Not without a new vehicle, a new landing, a new risk. So the landing site has to be chosen like you are choosing the location of a harbour, or a railroad junction, or a city's first well. With caution, with surveys, with an acceptance that a decision made early echoes for decades. Even the simple act of stepping outside depends on location. A site with rough boulders and steep slopes turns every spacewalk into an injury risk. A site with fine drifting regolith may increase wear on seals and joints until maintenance becomes a daily ritual. A site with poor visibility to Earth complicates communications and forces reliance on relay satellites. And a site that is too far from accessible ice may require that all water arrive from Earth, making each kilogram of life support a line item on a manifest. So when people imagine a moon city, the image is often architectural, domes, tunnels, habitats linked like beads, but the true skeleton is geographic. Where is the power? Where is the water? Where is the stable ground? Where can you land again and again and again without blasting your own base with dust? That last point is quietly important. If Starship is the building, then you still need additional Starships to deliver more systems, more people, more equipment. And rocket landings throw energy into the ground. They disturb the surface. They lift dust. They can sandblast nearby hardware. So the right place is not just a single spot, but a layout. A zone where landings happen. A zone where habitats rest, routes between them, and an understanding of how exhaust and regolith will behave over time. It is almost like learning weather patterns, except the weather is made by your engines. And this is why the idea carries that subtle tension. Turning a ship into a settlement sounds like simplification, and in many ways it is. You bring one large object, and you live inside it. But by doing that, you commit. You anchor your future to a location you have chosen, on a world where the smallest details of terrain and sunlight can quietly decide whether a base feels stable or feels constantly on the edge of failure. But a repurposed Starship is only useful if it lands in the right place, and on the moon, location may determine whether a settlement thrives or fails. That is why the lunar South Pole keeps returning to the conversation, again and again, as if the moon itself is quietly pointing toward it. For a long time, most people imagined the best place on the moon as the easiest place to land, a wide, flat plain near the equator, bright, open, familiar in old photographs. But a permanent settlement does not choose a site the way a short visit does. A permanent settlement is not looking for a postcard. It is looking for a neighborhood with utilities. And on the moon, utilities are not evenly distributed. Not all places on the moon are equally useful, because the moon does not treat sunlight, temperature, and accessibility equally. The equator is punished by the long lunar day, about 2 Earth weeks of sunlight, followed by about 2 Earth weeks of darkness. That cycle is not just inconvenient, it is an engineering burden. If you want constant power there, you either build enormous energy storage or you bring a power source that does not depend on light. Both options are possible, but neither is simple. Meanwhile, some regions near the poles behave differently. Not because the poles are warmer, they are not, but because the geometry of the sun changes there. At the South Pole, the sun never climbs high in the sky. It circles low, like a lantern held near the horizon. And that one fact rearranges everything. It creates places where light is almost always present, and nearby places where darkness is almost always present, sometimes only a few kilometers apart. So the South Pole becomes, in a very practical sense, the moon's most valuable neighborhood for long-term living. It is a convergence point. Energy, communication, and resources cluster there more tightly than almost anywhere else. Energy, because ridges and crater rims can receive sunlight for long stretches. Communication, because some high points can keep Earth in view more often, reducing the need to hide behind mountains and wait for a radio window. And resources, because cold, shadowed pockets can preserve volatiles, especially water ice, in a way most of the Moon cannot. This is why the maps of proposed landing sites keep circling back to one name: Shackleton Crater. It sits very close to the South Pole, a crater that in many ways is less about the hole in the ground and more about the terrain around it. Shackleton itself is deep. Its floor is in darkness for extremely long periods, but its rim and nearby high ground can catch that low circling sunlight. And this is where the geometry of light becomes almost architectural. If you stand on a high ridge near the South Pole, you are not watching the sun rise and set in the normal way. You are watching it skim, moving sideways, sometimes dipping behind a distant ridge, then returning. For a base, that can mean something priceless, not perfect, not continuous, but near continuous sunlight. Long runs of power, without the harsh rhythm of 2 weeks on, 2 weeks off. And power on the Moon is not a luxury. Power is air circulation, water processing, thermal control, computers, communications, mining equipment, life support that does not pause because the sky went dark. Near constant sunlight changes how large your batteries need to be, how heavy your storage systems are, and how much you must bring from Earth, just to keep the lights on. There is another advantage, quieter but equally shaping: the view of Earth. From many locations on the Moon, Earth hangs in the sky like a fixed point, but not everywhere has a clean line of sight. At the poles, terrain can block Earth, and some sites spend long periods with Earth hidden behind crater walls. So the best locations are often not the lowest, but the highest. If your habitat sits on or near elevated terrain, your antennas can maintain communication more consistently. That reduces dependence on relay satellites, and it reduces the number of failure points. It is not that relay satellites are impossible. They are an expected part of long-term lunar operations, but every extra link in a chain is one more thing that must work, in an environment that does not forgive neglect. So near Shackleton, the appeal is not just a romantic idea of building on a crater rim. It is the practical alignment of geometry, sunlight for power, and a better chance of seeing home most of the time. But the South Pole's strangest asset is not on the sunlit ridges. It is inside the shadows. The Moon's poles contain what scientists call permanently shadowed regions, crater interiors that sunlight almost never reaches, because the sun stays low, and the crater walls act like a collar. If you step into those shadows, you step into a different thermal world. Without sunlight, the surface cannot warm. And because the Moon has almost no atmosphere, there is no air to carry heat around. No wind, no convection, only the slow exchange of radiation. The result is that some of these shadowed pockets, especially deep ones near the poles, are among the coldest places in the solar system. Cold enough that certain materials do not behave normally. Cold enough that molecules can become trapped, sticking to grains of dust, and staying there. Not for days, not for centuries, but potentially for billions of years. These permanently shadowed craters are often described as cold traps, and the name is accurate. They trap volatiles delivered by comet impacts, by meteorites, and possibly by chemical processes in the lunar soil itself. Over immense time, that trickle can accumulate, and among the volatiles that matter most is water. Not rivers, not lakes, but water ice, mixed into regolith like dirty snow, or distributed in patches, or locked into grains. We do not yet know the exact form in every location, and that uncertainty matters, but multiple lines of evidence suggest it is there. Remote sensing, neutron measurements, radar hints, and the logic of cold physics. It is one of those scientific situations where the picture is not complete, yet the outline is persuasive. And if the ice is real and accessible, it changes the difference between an outpost and something closer to a civilization. Because water is not merely something you drink. Water is breathable air once you process it. Water is hygiene, which is not comfort but infection control. Water is agriculture support, not necessarily fields and forests, but small, controlled systems where plants recycle carbon dioxide and add food to a supply chain. Water is industrial chemistry, a solvent, a reactant, a way to make processes simpler, and water is thermal management. In a habitat, water can store heat, move heat, and help smooth the violent swings between sun and shadow. So when engineers talk about lunar ice, they are not just imagining survival, they are imagining multiplication. Every kilogram of water you do not launch from Earth is a kilogram that can be replaced by something else. More tools, more insulation, more spare parts, more scientific instruments, more capacity to grow. Local water access becomes a threshold. Before local water, every expansion is constrained by supply flights, and the settlement remains fragile. After local water, the settlement can begin to breathe on its own schedule, still dependent on Earth in many ways, but less tightly leashed. And then comes the next step, the one that matters deeply to SpaceX's style of logistics. Water can be split. If you apply electricity to water, in a process called electrolysis, you separate it into hydrogen and oxygen. This is established chemistry, not speculative. It is energy intensive, meaning you must have abundant power, but the basic reaction is well understood. And those two products, hydrogen and oxygen, are not only life support consumables. Oxygen is what you breathe, but it is also the oxidizer in many rocket engines. Hydrogen can be used in some propulsion systems and can support industrial processes. Even if a settlement does not choose hydrogen as its primary fuel, oxygen alone can be enormously valuable. For some spacecraft designs, oxygen is the heavier fraction of propellant by mass, so producing oxygen locally, even if other fuels still arrive from Earth, can reduce the total amount that must be launched. This begins to close the loop. Instead of every mission being a one-way delivery, the Moon becomes a place where vehicles can refuel, where tanks can be topped up, where a transportation network begins to look less like heroic expeditions and more like regular shipping. If you can make propellant at the Moon, even in modest quantities at first, you change the economics of moving around cislunar space. Trips between Earth orbit and lunar orbit, between lunar orbit and the surface, between the Moon and nearby space stations or depots, start to feel less like singular events, and more like a route. A difficult route, but a route. And this is the deeper logic behind choosing the South Pole. It is not only about landing somewhere interesting, it is about landing where sunlight and ice sit close enough together that a base can run machines, and those machines can produce water, air, and potentially fuel. But there is also a claim that hovers around this vision, a strategic idea often associated with Elon Musk's style of thinking. The suggestion, carefully stated, is that the Moon may contain more than it first appears. Not just water, but enough of the key elements, including carbon and hydrogen, to support a self-growing settlement over time. In that framing, the Moon is not merely a barren rock, it is a starting kit, a place with hidden inventories. It is important to treat that as a direction, not a solved engineering fact. Because carbon on the Moon is not known to be abundant in the way it is on Earth. Hydrogen is present in polar regions, but distribution, concentration, and accessibility are still being mapped. And even if the atoms exist, the question becomes, how hard is it to collect them, and at what energy cost, and with what equipment, and how often do systems break in dust, vacuum, and cold? Resource sufficiency is one of the great unknowns in any lunar city vision. It is not only a question of science, it is a question of operations. How many excavators? How many processing units? How many replacement parts? How many years of gradual improvement before the local economy begins to sustain itself? A settlement can fail, not because the science was wrong, but because the maintenance burden grows faster than the capability to maintain. So the South Pole, and Shackleton's neighborhood in particular, is chosen because it offers a rare chance, a tight clustering of advantages, in a world where advantages are usually scattered. Near continuous sunlight, nearby cold traps, a better line of sight to Earth, and the possibility, not the promise, of turning local ice into life support and logistics. And yet, even here, with all these gifts arranged on the map, there is a calm, lingering restraint that must remain. Still, sunlight and ice alone do not make a city, because the Moon remains a harsh, abrasive, and biologically unforgiving place to live. The difficulty is easy to underestimate, because the pictures look clean. A grey horizon, a black sky, a bright sun, and the quiet illusion of stillness. But the Moon is not gentle. The ground is not sand, not soil, not anything shaped by water or wind. It is regolith, a layer of shattered rock and glass made by impacts over unimaginable time. Each grain has sharp edges because nothing rounds it off. It clings to surfaces, it works its way into joints, it scratches seals, it irritates skin and lungs, and it carries static charge that makes it stubborn and strange. A city needs doors that close, filters that keep working, bearings that keep turning, fabric that does not fray into dust. Even a small outpost needs these things. A growing settlement needs them constantly, every day, for years. And at the South Pole, the environment adds its own quiet pressure. Light and shadow sit close together there, but they also create sharp thermal boundaries. In sunlight, hardware can heat quickly. In shadow, temperatures fall into deep cold. If a rover crosses from a sunlit ridge down toward a shadowed crater, it may move through a gradient that feels almost eerie in its abruptness. Materials expand and contract, lubricants behave differently, batteries lose performance, metal becomes brittle, plastics can crack. The same geography that offers opportunity also demands careful design and careful habits. Even the nearly continuous sunlight, the thing that makes those ridges so valuable, has its own complexity. The sun stays low. That means long shadows, low-angle illumination, and power systems that cannot assume the sun is overhead. Solar panels may need to be placed vertically, or tilted, or mounted on towers. Cables may need to run across uneven ground, from the bright ridges down toward the processing sites, and those cables must survive abrasion, radiation, and cold. Energy is there, but it is not simply waiting in the open. It must be collected, managed, protected, repaired. Then there is the ice, the treasure of the permanently shadowed regions, and also a reminder that the moon hides what it offers, because digging in those cold traps is unlike digging anywhere humans have worked before. You are mining in darkness, at temperatures so low that ordinary machinery may struggle. You may need lights, but lights add heat. And heat changes the properties of the material you are trying to handle. You may need to keep equipment warm enough to function, while keeping the environment cold enough to prevent volatile loss. You may need to move icy regolith out of shadow, but moving it into sunlight can cause sublimation, turning ice directly into vapor, a slow leak into vacuum. So the simplest plan, scoop, heat, capture, becomes a chain of engineering compromises, and each compromise becomes a maintenance schedule. This is why careful language matters. The South Pole is not a promise, it is a concentration of chances. The best neighborhood on the moon still forces you to earn everything you use. Power must be harvested, water must be extracted, oxygen must be processed, fuel must be manufactured, and every machine doing that work must itself be protected from the very environment it is built to exploit. There is also the quiet psychological dimension, often left out of technical diagrams. If Earth is visible more often from certain high points, that helps communications. But it also means that for someone living there, home can hang in the sky, small, distant, and constant. A reminder, and sometimes an unsettling one, that the nearest rescue is not over the horizon, it is days away, at best. This is not drama, it is simply distance, made emotionally real. So when we talk about Musk's strategic claim that the moon might contain enough key elements to support a self-growing settlement, it helps to add one more layer of caution. Even if the atoms are present, even if the chemistry works, the moon still has to be lived in. A civilization is not only a spreadsheet of resources, it is a system that can tolerate failure and keep going. It is spare parts and trained hands and time. It is the slow art of making routine out of risk. And that is why the South Pole changes the equation, but does not finish the calculation. It brings sunlight close to shadow, and shadow close to ice, and ice close to the idea of fuel, and fuel close to regular travel. It tightens the web. It makes the moon feel slightly less like a destination, and slightly more like a place. Still, sunlight and ice alone do not make a city, because the moon remains a harsh, abrasive, and biologically unforgiving place to live. The moon remains harsh, abrasive, and biologically unforgiving. And one reason it surprises people is that it is not simply space, but closer. It is its own category of difficulty, quietly more demanding than the kind of living we have already practiced. On the International Space Station, humans live in orbit, wrapped in layers of engineering, but also wrapped in Earth. The station is high above the atmosphere, and yet it still moves inside the broad reach of Earth's magnetic field, a region that helps deflect many charged particles from the Sun and some of the high-energy cosmic radiation that passes through our neighborhood of the galaxy. There is also a thin but real advantage from Earth itself, occupying half the sky, blocking a portion of what would otherwise arrive from below. Even the logistics are different. Because low Earth orbit is close, vehicles come and go. New parts can be delivered. Urgent problems can be answered with fresh hardware and fresh planning. And if something goes badly wrong, return is possible, within hours. The Moon does not offer that kind of gentle safety net. On the Moon, there is no global magnetic shield. There is no thick atmosphere to break apart incoming debris, or to soften the sharp edge of radiation storms, or to carry heat around the planet for you. There is only the direct physics of sunlight, and vacuum, and the steady, patient rain of particles, some harmless, some not. In low Earth orbit, a lot of survival depends on operational routine, checklists, procedures, training, the careful culture of a crewed program. On the Moon, routine still matters, but survival leans more heavily on deliberate engineering, because the environment is less forgiving of small mistakes. A seal that would last for years in orbit might fail sooner when filled with abrasive dust. A habitat wall that is adequate for an orbital module may be unsettlingly thin when placed under open lunar sky, and the distance changes everything. Even with good vehicles, rescue is not a simple option. So the logic of a lunar base becomes clear. You do not just operate a habitat, you build an environment that can endure. That is where the idea of burial begins, not as a dramatic flourish, but as a practical response to physics. If a Starship-like vehicle is used as an early habitat, one of the most often discussed countermeasures is to cover it with lunar soil. Not a dusting, but meters of regolith. A common target in serious discussions is on the order of 5 meters, because that is the scale where shielding begins to look meaningful against both radiation and impacts. Regolith is the Moon's surface layer, a mixture of crushed rock, powdered minerals, and broken glassy fragments, produced by billions of years of micrometeorite strikes. It is not soft, like Earth soil. It is more like ground-up ceramic. But it has mass, and mass is what you want between people and space. Radiation is complicated. There are different kinds, and not all shielding works equally well against all of them. But in general, if you place enough material overhead, you reduce the dose from solar particle events, and you lower the steady background from many cosmic rays. You do not erase the problem, yet you can shift it from impossible for long stays to managed with careful limits and monitoring. Burial also helps with micrometeorites. Most micrometeorites are tiny, grains and pebbles moving at extreme speed, too small to track, but energetic enough to punch and pit and slowly damage exposed surfaces. On the station, micrometeorite shielding is a constant concern, but the station is built with that in mind, and it is maintained with regular inspection and replacement. On the Moon, a habitat that sits exposed accumulates risk day after day, with fewer chances for quick repair. A regolith blanket becomes a kind of quiet armor. It turns an exposed vehicle into something closer to a bunker, not in a military sense, but in the simple sense of being buffered from the sky. And that transformation matters. A Starship hull on the surface is a temporary shelter, a place you can survive. For a while, a Starship hull under several meters of regolith begins to resemble a plausible long-duration home, something that can remain occupied, while other structures are assembled around it. Of course, burial is not a single action. It implies equipment, bulldozers or robotic movers or conveyor systems, and careful structural planning. Because regolith is heavy, you do not want to place uneven loads or create pressure points or bury important hatches, vents, and radiators without alternatives. And the moment you bury a habitat, you commit yourself to a different kind of architecture, one where life support becomes more central, because you have fewer easy ways to vent heat, or swap external components, or make quick changes on the outside. Then there is the thing almost every lunar veteran talks about, with a tone that is calm but never casual. Dust. Lunar dust is strange. On Earth, dust grains have usually been rounded by wind and water, softened over time. On the Moon, there is no liquid water, no air, no weathering in the familiar sense. So the dust remains sharp, jagged, splintered, like tiny broken shards, It also becomes electrically charged. Sunlight knocks electrons loose, the surface can develop local electric fields, and dust can cling in ways that feel almost alive, as if it is searching for seams. The Apollo crews described it as persistent, getting into everything, smelling like burnt metal when brought inside, and irritating to eyes and lungs. This is not a small detail. It becomes an operational threat. Dust grinds at seals, and seals are what separate life from vacuum. Dust abrades suit joints, and suit joints are what allow people to move without tearing the pressure garment. Dust coats optical surfaces, cameras, sensors, solar panels, slowly reducing performance. Dust can foul mechanical bearings, clog filters, and create friction where friction cannot be allowed. And if it enters the habitat atmosphere, it becomes something even more personal, a lung hazard. Fine particles can lodge deep, and because the dust is sharp and chemically reactive in some forms, it raises concerns about inflammation and long-term damage. It is not certain exactly how severe the health impacts would be over years, because we have not yet run that experiment. But the uncertainty itself is part of the problem, a quiet risk you must engineer around. So a serious lunar base needs dust control, not as an accessory, but as a core system. It starts outside, with disciplined procedures for leaving and returning. You minimize how much dust comes in on suits by using suit ports or external airlocks designed for brushing and vacuuming, or electrostatic cleaning surfaces, or gas jets that blow dust away before it reaches seals. You design pathways and work zones to reduce tracking. You accept that every extravehicular activity, every walk outside, is not just a mission task, it is a contamination event that must be managed. Inside, you need filtration, air circulation designed to capture particles, surfaces that can be wiped down, equipment laid out so it can be cleaned, and maintenance routines that feel almost obsessive. Because on the Moon, small neglect becomes cumulative, and cumulative becomes failure. Even if you solve radiation and dust, there is another slow pressure, one that does not feel dangerous at first, because it is happening inside the body. Low gravity. The Moon's gravity is about 1/6 of Earth's. That sounds comfortable, almost playful, until you remember the human body is a system built around load. Bones stay dense because they are stressed. Muscles stay strong because they work against weight. The cardiovascular system adapts to gravity, fluids settle, pressure gradients exist, and the body quietly uses those gradients as part of its normal functioning. In microgravity, astronauts lose bone density and muscle mass, even with exercise. On the Moon, gravity is not zero, so it may be somewhat better, but it is still far below what biology expects. Over long stays, you would still anticipate muscle weakening, bone loss, changes in balance and coordination, and potential impacts on the immune system and vision, areas where spaceflight has shown worrying signals. This means a lunar settlement cannot treat exercise as optional. It becomes medical infrastructure. You would need serious hardware, resistive machines that can mimic lifting heavy loads, treadmills or running systems, perhaps cycle devices, and the time in the schedule to use them consistently. You also need diagnostics, monitoring bone density, blood markers, injury risk, and the ability to respond early rather than late. If you are designing a base, you design for health maintenance the way you design for oxygen. You allocate volume, power, spare parts, noise isolation, and redundancy. Because the body is part of the settlement, and if it degrades, the settlement loses capability. This is one of the more subtle shifts, from exploration to habitation. Explorers can endure a decline, knowing they will go home. Settlers need a stable baseline, or the whole project becomes a slow medical emergency. And that leads into the hidden heart of any lunar city, life support. People often imagine a base as a shape, a cylinder, a dome, a landed ship. But the visible walls are only the beginning. The real architecture is the invisible circulation of essentials: air processing, water recycling, thermal management, power routing, and fault tolerance. Air is not just oxygen. You must remove carbon dioxide, control humidity, scrub trace contaminants, manage odors and particulates, and keep the mix stable under changing crew activity. A base with plants may help, but plants are not automatic life support. They are living machines with their own demands: light, water, nutrients, pathogens, and failure modes. Water recycling is equally central. Every kilogram you do not have to import is a kilogram you do not have to launch. You capture moisture from breath, from hygiene, from cooking. You purify it, store it, and protect it from contamination. You also manage waste, solid and liquid, not as something to discard, but as a resource stream and as a biohazard if mishandled. Thermal management may be the most counterintuitive. In vacuum, you cannot cool by blowing air. You cool by radiating heat away, and radiators need exposure to cold space. But if your habitat is buried under regolith, you have traded radiation shielding for thermal complexity. You may need heat pipes, conductive paths, external radiator panels placed away from dust, and careful control to avoid overheating systems that cannot tolerate high temperatures. At the same time, you must prevent freezing, because many systems fail when ice forms where it should not. Power routing ties everything together. Solar arrays on ridges, batteries, perhaps fuel cells, cables protected from abrasion, switchgear designed for reliability, and the ability to isolate failures without blacking out the base. And always, redundancy. Not just one filter, but two. Not just one pump, but backups. Not just one airlock, but a secondary path. Because on the moon, a broken part is not an inconvenience. It can be a countdown. When you view it this way, the settlement is not a building, it is a metabolism. The walls hold pressure. But life support makes that pressure meaningful. It turns empty volume into breathable space, turns cold rock outside into warmth inside, turns a collection of humans into something that can persist and even work. And that difference between surviving and living is where the long future begins. A short-stay module is designed around emergencies. How fast can you seal? How long can you last on stored supplies? How quickly can you leave? A permanent human environment asks different questions. How do you sleep well for months? How do you reduce chronic stress? How do you create privacy, quiet, a sense of normal time in a place with long days and long nights? Or, near the poles, a sun that skims the horizon like a watchful instrument? How do you build reliability, not just by adding stronger parts, but by creating maintenance routines, training, documentation, and a culture that treats small repairs as daily hygiene? And then there is psychology, the part that can sound soft until you realize it is operational. People need variation. They need spaces that do not always feel like equipment bays. They need light that supports circadian rhythms, colors that are not only grey and white, sounds that are not only fans and pumps. They need communication that feels immediate, even when physics imposes delay. They need shared rituals, meals, work schedules, holidays, the gentle scaffolding of civilization. This too is engineered. Comfort becomes a safety factor, a base that supports mental stability, reduces errors, reduces conflict, reduces the slow erosion of attention that leads to accidents. So the build-out would likely be gradual. First, a buried shelter that is simply safer than the surface, then add-on modules, workshops, storage, greenhouses, medical capability, better radiation shelters, more robust power, more space per person, more privacy, more reliable recycling, and systems designed for repair with local tools. Practicality and habitability grow together, because each makes the other possible. A comfortable crew maintains equipment better, and reliable equipment gives the crew the calm margin needed to live well. On the moon, that balance is not luxury, it is function. And once survival becomes manageable, the next question is no longer whether humans can stay on the moon, but whether a real lunar economy can begin there. A real lunar economy is not a slogan, it is a set of physical transactions that only make sense if the environment stops constantly trying to erase the people doing them. And it is worth noticing how many of the dangers we just described are not dramatic, not explosive, not loud. They are slow, powdery, invisible like a quiet corrosion of margins, radiation that accumulates without sensation, dust that works its way into hinges, bone that thins a little each month. A pump that drifts out of spec, a filter that loads up. A lunar base fails, most often, by subtraction. So when people talk about building a city on the moon, the word city can feel too big, too human, almost unrealistic. But in engineering terms, a city begins the moment the habitat stops being an exception and starts being a system that can be repeated, expanded, and maintained by the people who live inside it. That is why the buried Starship concept, or any buried habitat concept, is so important. It is not about romance. It is about turning the sky from an enemy into a roof you do not have to think about every minute. When you put several meters of regolith above a pressure vessel, you change the psychology of work. You can plan months ahead instead of hours. You can accept that a solar storm might happen without treating it like the end of the calendar. You can schedule maintenance like a normal profession, instead of an emergency ritual. And in the background, the life support system keeps doing what civilization has always required, taking chaos and making it repetitive, breath after breath, sip after sip, degree after degree. There is a strange comfort in that, and also a subtle unease, because it reveals what we usually forget on Earth. That comfort is manufactured. It is designed. It is maintained. On the Moon, nothing is free. Even the simple act of opening a door is an event with consequences. Airlocks become customs offices, not for people, but for dust, and for loss of air, and for the wear on seals that must survive thousands of cycles. Storage becomes strategic, because everything imported is expensive, and everything produced locally is precious. Spare parts become a form of currency, because repair is life. And the base itself, if it is to become more than a camp, needs to shift from dependence to capability. That shift can be slow, almost imperceptible. At first, you bring what you need. Then, you bring what you need to make what you need. Tools, feedstock, machines that can shape metal, machines that can sinter regolith into bricks or tiles, machines that can test materials and certify pressure fittings and check welds and verify that a patch is not just a patch, but a safe repair. In that world, engineering becomes culture. Checklists become tradition, calibration becomes routine, and people begin to live. Not in spite of the Moon, but in collaboration with its rules. The lunar day and night cycle, or the near-constant grazing sunlight of polar regions, becomes part of scheduling. Power availability shapes work, like weather once shaped farming. Thermal constraints shape architecture, like seasons shape cities on Earth. And because the outside is so hostile, the inside begins to matter more than ever. Not just function, but meaning. A wall panel that can be removed and replaced, and cleaned, is not only convenient, it is psychological relief. A small greenhouse corner, even if it is mostly practical, is also a reminder of growth. A private sleeping space, with light that can dim gradually, is not indulgence. It is cognitive stability. Because the Moon does not only attack hardware, it pressures attention. It tests patience. It makes every mistake expensive. In a place like that, habitability is not decoration. It is error reduction. It is safety engineering, expressed as design. And as these systems become stable, as the regolith shielding holds, as dust stays mostly outside, as bodies stay strong enough to work, as water loops close more tightly, as power outages become rare rather than expected, something subtle happens. The base stops feeling like a mission, and starts feeling like an address. Not because it is easy, but because it is repeatable. And once survival becomes manageable, the next question is no longer whether humans can stay on the Moon, but whether a real lunar economy can begin there. A lunar economy is a quiet phrase, and yet it is a very different creature than a lunar expedition. An expedition is a story with an ending, a launch, a landing, a flag, a return. An economy is not impressed by endings. It insists on continuity, on supplies arriving when they are needed, on repairs being possible, on replacements existing before failures happen. It demands a kind of patience that does not fit neatly inside a political term or a single budget cycle. That is one reason traditional space programs struggle to stay permanent, even when the science is strong, even when the engineering is excellent, even when the people involved are sincere. Government programs are built inside changing priorities, and they are vulnerable to them. A new administration arrives, a legislature shifts, a crisis pulls attention and funding somewhere else, and the long arc of a settlement gets bent. Not always because anyone is careless, but because human institutions are rhythmic. They pulse with elections and headlines, and the Moon does not. On the Moon, the air does not care which party won, the dust does not care which committee is in charge, and radiation does not wait for a continuing resolution. A permanent settlement needs commitments, measured in decades, not in news cycles. It needs a model that survives beyond election timelines, something that can keep building, even when the emotional thrill of the first landing fades. This is where the contrast becomes sharp between symbolic missions and infrastructure that compounds. A symbolic mission can be astonishing. It can expand knowledge. it can inspire, and then it can end. Compounding infrastructure is less dramatic, but more powerful over time. A landing pad that reduces dust damage, a pressurized tunnel that connects habitats, a power plant that runs reliably through long shadows, a standardized docking port, a warehouse of spare parts, a set of tools that can machine and test components on site. Each one makes the next step easier. Each one reduces the cost of the next shipment, reduces the risk of the next repair, reduces the fragility of the whole system. In that sense, the question of a moon city is partly an economic question, and not just a transportation question. If the base always consumes resources, and never produces anything valued on Earth or in space, it will remain a fragile project, dependent on someone's willingness to keep paying, year after year, through every change of mood and policy. But if a base can pay for itself, even partially, it becomes harder to cancel. Not because it is romantic, but because it is useful. The argument is not that the moon will quickly become profitable in the ordinary sense. The moon is too harsh, and the early stages are too expensive. The argument is something quieter, that a permanent lunar base could create economic returns, enough to build a feedback loop. At first, those returns might be small and not always in cash. They might be in services, in capabilities, in data that is valuable to industry, in time saved, in risk reduced. One possibility is research space leasing, a simple idea with a technical edge. If you can offer a pressurized lab module, power, thermal stability, clean handling, and reliable communications, then universities, private companies, and international partners can rent time and volume, the way they rent a facility on Earth. They might run experiments in low gravity, test pharmaceuticals, study how materials solidify, observe how fluids behave, or validate life support components before committing them to longer missions. Another possibility is industrial experimentation, which is different from research because the goal is repeatable production. If you can demonstrate that certain manufacturing processes work better in vacuum, or at low gravity, or in extreme thermal conditions, then the moon becomes a testing ground, a place where failure is expensive, but success is transferable. And then there is fuel production, a phrase that sounds simple until you remember what it means. If water ice can be mined and purified, and if power is available to split that water into oxygen and hydrogen, and if those cryogenic propellants can be stored with acceptable losses, then the moon could, in principle, produce rocket propellant. Not infinite amounts, not quickly, and not without large hardware and careful engineering, but enough to matter for certain kinds of operations. Even oxygen alone is significant, because oxygen is usually a large fraction of chemical propellant by mass. And beyond fuel, there are infrastructure services, things that do not look glamorous, but are the skeleton of an economy: navigation beacons, surface communications networks, radiation monitoring, emergency shelters, spare capacity in power and life support, repair depots, waste processing, landing pads, and storage. A base that can provide these services, even to its own expansions, begins to behave like a port, not a campsite. Revenue matters for sustained presence, because it changes the logic of survival. It makes plans less dependent on a single patron and more dependent on performance, on reliability, on delivering value. That can be unsettling in its own way, because it imports the pressures of markets into a place where mistakes can be fatal. But it is also one of the few known mechanisms that can keep large projects alive across generations. The next shift is scale. Most people imagine a moon base as a few heroic landings, a handful of modules, a small crew, and the careful counting of every kilogram. That is how nearly all lunar thinking has worked, because that is what launch costs and vehicle limits forced. But a settlement, even a small one, is an avalanche of mass. Not a few landings, but the movement of enormous amounts of equipment and eventually people. Pressure vessels, radiation shielding, power systems, excavation machinery, processing plants, spare parts, replacement seals, cables, valves, computers, batteries, water tanks, habitat expansion kits, and all the hidden bulk of civilization, the things no one photographs. The difference between a mission and a city is not just the presence of people, it is the presence of redundancy. And redundancy is heavy. This is where reusable heavy lift changes what can be imagined. If a very large vehicle can fly, deliver cargo, and return to be flown again, the cost per ton can drop, not automatically, not without a lot of operational maturity, but enough to change behavior. You stop treating each shipment like a museum artifact and start treating it like freight. And freight is what builds infrastructure. Repeated cargo delivery is also what opens the door to many participants, not just national astronauts. If transportation becomes frequent, if schedules become predictable, if payload integration becomes routine, then the Moon can host more than government crews. It can host commercial engineers, geologists, medical researchers, construction specialists, robotics teams, even artists and writers, not as a spectacle, but as part of an expanding workforce. Not everyone at once, not quickly, but as a gradient. Accessibility is not only about ticket price, it is about reliability. When flights are rare, everyone is special. When flights are frequent, systems become standardized, and standardization is the beginning of scale. As that scale appears, another region comes into focus, a region that is not a planet, but a corridor. Cislunar space, meaning the space between Earth and the Moon, including the many possible orbits and transfer paths that connect them. It is easy to picture Earth and the Moon as separate destinations, but the space between them can become an environment of its own, filled with trajectories, platforms, and infrastructure. In a mature scenario, a lunar settlement does not only serve itself, it supports communications by hosting relay stations on the surface and by supplying power and maintenance for orbiting assets. It supports fueling, not just at the surface, but through depots placed in useful orbits, where vehicles can top off propellant, or at least oxygen, before heading onward. It supports manufacturing by exporting processed materials, or specialized parts, to platforms in orbit where assembly is easier, and where products can be shipped without climbing out of Earth's deep gravity well. And it supports scientific infrastructure. Telescopes placed on the far side for radio quiet, instruments placed at stable thermal locations, and long baseline experiments that benefit from the Moon's size and stability. In this view, the Moon is not a remote endpoint. It is a logistical and industrial node. A port at the edge of a gravity well, a place where you can turn local dirt and ice into useful mass and useful momentum. Once you think this way, you start to notice something almost eerie about how much energy is spent on Earth just lifting raw materials out of the gravity well before you can even begin building in space. If you can source some fraction of those materials from the Moon, where gravity is weaker, the architecture of space industry shifts. That brings us to an idea that often appears in the background of lunar discussions. Quietly, because it sounds both simple and strange. A mass driver. In plain language, a mass driver is a machine that throws things, not with a chemical explosion, but by accelerating cargo along a track using electromagnetic forces. On the Moon, where there is no air resistance and where escape velocity is lower than Earth's, a mass driver could, in principle, launch containers of material into orbit, efficiently, repeatedly, without needing a full rocket for every shipment. This is not an easy device to build. It would need extreme reliability, precise guidance, careful safety zones, and robust power. It would also introduce new hazards, because a misaimed payload is not a small mistake. It is a high-speed object that keeps going. So this remains speculative, more a concept than a near-term plan. But it shows the direction of thought. If lunar material can be moved off the surface cheaply, then manufacturing can migrate outward. Some manufacturing might stay on the Moon, especially things like shielding bricks, glass, simple structural components, and oxygen production. But other manufacturing could happen in orbit, where you can assemble very large structures without needing them to survive a launch from Earth. Solar power stations, large antennas, radiators, habitats with rotating sections for artificial gravity experiments and industrial platforms. Lunar-based manufacturing could support orbital systems by supplying bulk mass and by supplying consumables, and perhaps, over time, by supplying refined metals. And here, a modern twist enters. Elon Musk has occasionally hinted, not always with detail, that advanced automation and artificial intelligence could change the economics of building. The underlying idea is familiar. If machines can do more work with less supervision, then labor constraints loosen. In an environment where human time is precious and life support sets strict limits, robotic construction, autonomous mining, and automated maintenance become more than convenience. they become the only path to millions of tons. Artificial intelligence does not eliminate the harshness of the moon. It does not make seals last longer by itself. It does not stop dust from being sharp, but it can help coordinate fleets of machines, schedule repairs, detect failures early, optimize power usage, and keep a complex industrial system from drifting into chaos. If that works, it is an industrial opportunity, not just a scientific one. A lunar settlement could become, in part, a proving ground for semi-autonomous industry, a place where the line between factory and habitat blurs. And as all of this develops, it is natural to ask about Mars, because Mars has always been the larger horizon in Musk's public narrative. Here we have to be careful, because timelines are fluid, and public statements evolve. The more cautious view, based on the sheer difficulty, is that early attempts to send cargo and perhaps uncrewed systems might begin in the late 2020s, with human landing more plausibly pushed into the early 2030s. Even that would be extraordinarily ambitious. Mars is far, launch windows are constrained, entry and landing are brutal at high mass, and rescue options are limited. The moon can help, but it does not magically solve those problems. It is also worth clarifying something practical. Space missions to Mars do not necessarily route through the moon. Even if the moon can produce propellant, lunar fuel availability is likely limited in the early decades, especially hydrogen, because storing hydrogen is hard, and mining and processing water at scale is not trivial. For many mission designs, it may still be more straightforward to launch Mars vehicles directly from Earth, refuel them in Earth orbit, and depart on the interplanetary trajectory without detouring to the lunar surface. So the moon is not always a gas station on the way to Mars. It is something more subtle, an accelerator of capability, a training ground for long-duration systems, a place to learn how to close life support loops, how to maintain power through extremes, how to build with local materials, how to manage dust and radiation, how to keep people healthy, how to run an emergency response when there is no nearby hospital, how to create resilience. Even if Mars ships still leave from Earth, a functioning lunar settlement makes those Mars ships more realistic, because the people building them, and the systems inside them, will have been tested in a place that is not forgiving. And perhaps that is the deeper logic, that a moon city is not merely a destination. It is a way of changing what humanity is capable of sustaining without constant heroic effort. Yet the story does not end with the moon, because the tools that make a lunar city possible may also reshape how humanity explores Mars and the rest of the solar system. If you step back and look at the whole picture, you can see why the word city keeps returning, even when the first reality will be smaller, more fragile, more like a workshop sealed against vacuum. A city is not defined by its skyline. It is defined by its metabolism, by the steady conversion of raw inputs into shelter, air, water, spare parts, repairs, and the quiet routines that keep people alive. On the moon, that metabolism begins as a supply line from Earth. But the long-term hope, the part that turns an outpost into something self-growing, is that the supply line slowly changes its contents. Less finished hardware, more specialized components. Less water shipped, more water extracted. Less oxygen delivered, more oxygen made. Not because it is elegant, but because the math becomes unforgiving otherwise. If every kilogram must be lifted from Earth forever, the settlement remains a tent held up by rockets. If some fraction can be produced locally, the settlement starts to have roots, and roots are what make permanence possible. The unsettling part, if you let yourself notice it, is that the moon does not reward improvisation. On Earth, if a system fails, a truck can arrive. A technician can show up with tools and a replacement. On the moon, a failure is a delayed shipment, a limited inventory, and a human body that cannot wait too long for air or pressure or heat. That is why redundancy becomes a culture, not just a design choice. Multiple power paths, multiple air processing loops, multiple ways to seal a habitat. And gradually, as shipments become routine, you would also see something that looks almost boring, but is actually profound. Standard containers, standard interfaces, standard valves, standard electrical connectors, standard docking rings. That sameness is what allows growth, because it allows different groups, different companies, different nations, even different generations of equipment to fit together without negotiation each time. Civilization is often just compatibility, extended over years. In the most practical sense, a self-growing settlement would be built from a few shared backbones. Power, first, because everything else leans on it. Solar arrays near regions with long sunlight, batteries and fuel cells for bridging darkness, perhaps eventually small nuclear systems. If politics and engineering allow, then communications, not just for streaming video, but for safety, coordination, and precise navigation for robots and landers. Then mobility, roads of compacted regolith or sintered surfaces, paths that reduce dust, routes that can be mapped and maintained. Then storage, because storage is how you buffer the unexpected. Water storage, oxygen storage, food storage, spare parts stored in sealed containers, protected from abrasive dust and thermal cycling. And then, slowly, industry. The first industry is almost always boring. Cutting, drilling, welding, machining simple brackets and pipes, making gaskets and fittings, building radiation shielding from local soil, turning loose regolith into solid blocks. It is not glamorous, but it is how you stop waiting for Earth. With each capability added, the next capability becomes easier. A landing pad reduces dust damage. Dust damage reduces maintenance. Reduced maintenance frees time and machines. Time and machines build more infrastructure, and the loop closes a little tighter. This is the compounding effect again. But now it is not just a philosophy, it is a mechanism. And once mechanisms exist, you can imagine many kinds of participation without needing everyone to be a national hero. A company might lease a pressurized module, because they need lunar vacuum next door to their lab, but still want shirt sleeves inside. Another might pay for a slot on a power and data network to run a long-term sensor array. A research group might buy time on a furnace or a metallurgy setup, because low gravity changes how alloys form. And some customers may never set foot on the surface at all. They might be in orbit, using lunar-supplied oxygen, or using lunar-sourced shielding bricks, or receiving raw material thrown up by some future launcher. In that sense, the Moon becomes part of a wider system, not an isolated camp. The cislunar region, that broad space between Earth and the Moon, starts to feel less like empty distance and more like an ocean with shipping lanes. You begin to picture depots in useful orbits, places where spacecraft can pause, refuel, repair, and reconfigure. You picture relay satellites, navigation beacons, and standardized docking ports. You picture stations that assemble structures too large to launch from Earth. Structures that once built, change what is possible. And then, even stranger ideas return, not as science fiction, but as engineering proposals. Mass drivers, electromagnetic tracks, quietly accelerating containers of oxygen, or metal ingots, or shielding tiles, and releasing them into carefully chosen trajectories. Again, this remains speculative. It would demand exquisite safety systems, because a thrown payload does not forgive error. But the reason people keep mentioning it is that it matches the Moon's peculiar strengths. No air, lower gravity, wide open space. If you can build a machine that throws useful mass into orbit reliably, you have built something like a bridge from a surface to the sky. And bridges change economies. At that point, manufacturing in orbit becomes more plausible, because the cost of bulk material is no longer chained entirely to Earth launch. Large radiators, truss structures, fuel tanks, pressure shells protected by thick shielding, and perhaps eventually rotating habitats for artificial gravity experiments could be assembled where launch stress is no longer the limiting factor. The Moon supplies some of the weight, Earth supplies the complexity. And around that interface, automation matters again. Not because it is fashionable, but because the system is too large for constant human attention. The machines must work while people sleep. They must notice cracks, leaks, bearing wear, and power anomalies before they become emergencies. They must coordinate like a slow swarm, patient, methodical, almost indifferent. It is a calm vision, but it contains a quiet tension, because you are trusting life support, industry, and transport to software and sensors in a place where rescue is not quick. And beyond all that, Mars remains what it has always been, the distant test of whether these skills truly transfer. A cautious reading of public timelines and of the actual engineering challenges suggests early cargo attempts might begin in the late 2020s, with human landing more plausibly in the early 2030s. Even those dates, if they happen, will be earned the hard way. It is also worth holding on to a simple practical point. Even if lunar propellant production becomes real, it may not be available at the scale needed to feed Mars missions soon, especially because hydrogen is difficult to store for long periods and difficult to handle without loss. So Mars ships may still launch directly from Earth, refuel in Earth orbit, and depart without touching the Moon. The Moon is not always a waypoint. It is an accelerator, a place to harden systems, teach organizations how to operate far from Earth, and build a culture of maintenance that does not rely on emergency deliveries. And if that culture takes root, it changes the meaning of future missions. They become less like expeditions and more like routes. Yet the story does not end with the Moon, because the tools that make a lunar city possible may also reshape how humanity explores Mars and the rest of the solar system. There is a quiet reason the Moon keeps returning to the center of these plans, even when the imagination is reaching for Mars and beyond. The Moon is close enough to be forgiving, in a way that deep space is not. Close enough that a broken valve, a cracked seal, a design mistake in a habitat wall does not have to become the end of a program. It can become a lesson, written down, tested again, and improved. In science and in engineering, progress often comes from reducing the penalty for being wrong. On Earth, laboratories do this with benches and prototypes, with controlled failures that teach you something. In space, the Moon can play a similar role, but at full scale. A place where you can learn the disciplines of off-world living while still being only days away, not months. That proximity changes the psychology of decision-making and the economics. If a cargo lander fails, you study the telemetry. You adjust the procedures, and you try again within a relatively short cycle. If a greenhouse system grows mold in a sealed volume, you can redesign the airflow, alter the filtration, change the lighting schedule, and send replacements without waiting for a rare planetary alignment. Iteration becomes possible, and iteration is a kind of gentle power. It also gives culture time to adapt, because a city is not just a pressure vessel and a power plant, it is routines, norms, habits, and shared expectations about safety, privacy, and responsibility. Living in a buried habitat beneath regolith, with air as a manufactured substance, forces a different relationship with waste, with maintenance, and with the idea of enough. On the Moon, those adaptations can happen gradually, with frequent contact with Earth, with rotation of crews, with the slow invention of customs that make life stable. In that sense, a lunar city is not merely a substitute for Mars, or a consolation prize. It is a rehearsal, a place to learn how to be a multi-world species, the way a harbour teaches a culture how to cross oceans. Not by guaranteeing success, but by letting failure become survivable, and therefore instructive. And as the Moon becomes more than a destination, another shift becomes clearer, one that is already happening quietly, without banners. The workforce of space will not be only human. Much of it will be robotic, and increasingly autonomous. This is not because humans are unimportant, but because space is full of delays, distance, and complexity that does not pause for human attention. Even around the Moon, where radio signals travel quickly, there are still blind spots, communication dropouts behind terrain, and time zones of operations on Earth that do not match lunar daylight. And once you move outward, to Mars and beyond, the delay becomes fundamental. Commands do not arrive instantly. They arrive late, sometimes very late. You cannot drive a rover the way you drive a remote-controlled car in your living room, because by the time you see the obstacle, the rover has already met it. So the machines must think ahead, in narrow ways, careful ways. We have already seen a version of this on Mars, with the Perseverance rover. In recent operations, Perseverance has used onboard systems to plan segments of its own driving, analyzing the terrain in front of it, detecting hazards like sharp rocks and steep edges, and generating its own waypoints, small stepping stones in a safe path, without waiting for each decision to be made by humans on Earth. It is not free will, and it is not imagination. It is closer to a quiet competence, a practical skill at moving through uncertainty. And that skill matters, because the future lunar workplace and the future Martian workplace will be filled with tasks that are too numerous, too repetitive, or too time-sensitive for constant human control. If you want a city, you need more than landings. you need roads, or at least reliable routes. You need cranes, haulers, excavators, surveyors, and inspectors. You need machines that can look at a slope, judge traction in fine dust, notice a wheel sinking, and back away before the situation becomes unrecoverable. You need systems that can inspect terrain for bearing strength, map boulder fields, and identify places where regolith is suitable for berms, for shielding, or for sintering into bricks. You need cargo movers that can haul heavy loads slowly, night after night, while the human crew rests. You need autonomous planners that can schedule power usage so that batteries are not drained at the wrong time, and critical heaters do not fail during a long lunar night, or during the shadowed cold of a polar crater. And you need monitoring. Constant monitoring, because risk in a sealed habitat is often not loud. It is a pressure leak that begins as a whisper. It is a chemical contaminant that accumulates invisibly. It is fatigue damage in a joint, or dust infiltration in a seal, slowly becoming serious. Smarter machines can reduce the human workload, not by removing humans from the story, but by protecting attention. A crew should not spend its best hours doing endless visual inspections or manually planning every short drive across a hazardous surface. Autonomous systems can take on the steady work, inspecting surfaces, moving cargo, planning routes, watching for anomalies, and flagging the few events that truly need human judgment. On the Moon, this ties directly into construction. If the plan involves using regolith as shielding, then regolith must be moved, piled, compacted, and shaped. If the plan involves turning landed spacecraft into habitats, then the surroundings must be stabilized and covered, and perhaps reinforced with structures that reduce micrometeoroid risk. If the plan involves building power networks near the South Pole, with cables, switching stations, and solar arrays placed along ridges, then machines must deploy equipment across kilometers of uneven ground, often in low sunlight, with extreme temperature gradients. And when the time comes to expand, to add new pressure volumes, new storage tunnels, new landing pads protected from dust plumes, the work becomes larger than any single crew can handle alone. In that light, the path to a lunar city may depend as much on machine competence as on rocket capacity. A reusable rocket reduces the cost of reaching the Moon, but competent autonomous systems reduce the cost of staying. They turn settlement from a sequence of heroic deployments into something more like ongoing operations. And operations, calm, repeatable operations, are what civilizations are made of. This is one of the deeper logics beneath a Moon-first approach, a logic that can sound almost too simple. Begin where the distance to failure is short, not because you expect to fail, but because you expect to learn. There is strategic wisdom in choosing a destination that can be reached, resupplied, and evacuated, without waiting for long windows of alignment. The Moon reduces the cost of failure and increases the speed of learning. A malfunction can be investigated while it is still fresh, while parts can still be shipped, while the same team is still together to remember the details. A habitat design can be refined across multiple missions and improved with real data, not just simulations. And over time, as systems become standardized, as docking ports become familiar, as spare parts become interchangeable, as procedures become routine, the settlement becomes less fragile. It is not that danger disappears, it is that the response becomes practiced. This is how robust systems are built, by letting reality correct you repeatedly, without letting reality destroy you. And when you imagine what it would feel like to live inside one of these early habitats, the view changes. Not the view through a window, necessarily, because many habitats may have few windows, for radiation reasons, and for thermal stability. The view changes in the mind. You picture a Starship hull, or a similar pressure vessel, lying on its side, or standing vertical like a quiet tower, and then slowly disappearing under a protective layer of lunar soil. You picture tunnels, airlocks, thick doors, and the soft, constant sound of fans. You picture lighting that imitates day, because outside the timing of day and night is unfamiliar, and the human nervous system still wants rhythm. And then you picture the moment you do see Earth. Not as a map, not as a concept, but as a bright disk hanging in the black sky, a place you used to think of as the world. From under meters of regolith, from a habitat where every breath is engineered, Earth might look both comforting and unsettling. Comforting, because it is home. Unsettling, because you can see how small it is and how much of life depends on a thin atmosphere, a fragile skin of air and water, glowing faintly at the edge. The moon changes, then, from a symbol of distance into a place of habitation. A place with addresses, with repair schedules, with stored food, with arguments over procedures, with birthdays celebrated in a gravity that feels like a gentle mistake. Not conquest, not a flag planted for a photograph, but continuity. A continuation of the ancient human habit of making shelter, then improving it, then inviting someone else inside. And if a first city beyond Earth does arrive, it may not arrive with a single dramatic moment. It may begin quietly as a chain of practical decisions that accumulate. Reusable launch systems that reduce cost, not to zero, but to something manageable. Habitat conversion, where landed vehicles become pressure volumes rather than discarded shells. South Pole resources, especially water ice in cold traps that can be turned into drinking water, air, and potentially propellant if the power and processing are sufficient. Shielding by regolith, not because it is elegant, but because it is there and because radiation is patient. Economic sustainability, not necessarily in the sense of immediate profit, but in the sense that the system can pay for its own continuation, through services, through research value, through industrial output, or through the simple strategic value of having a functioning off-world base. And always, fast iteration. The ability to test a design, learn from dust, learn from thermal cycling, learn from how materials actually age, and then adjust. Civilizational shifts often look dramatic in hindsight, but up close, they can look like procurement lists and standardized connectors, and routines that are written in calm language, and revised quietly after each near miss. The Moon City, in that view, is not a single event. It is a process of accumulation. One landing pad that becomes two, one habitat that becomes a small cluster, a power line extended another kilometer, a storage vault dug a little deeper, a robot that can lift a little more, a life support system that needs fewer emergency interventions, step by step, nearby. So the original question returns, with a different texture now. Does humanity's first true off-world civilization begin on the Moon, not as a base, but as a place where people can be born, work, age, and plan futures, without assuming they will soon return to Earth? The answer may not depend on fantasy, or on a single billionaire's confidence, or on one perfect rocket. It may depend on how well humans learn to build, adapt, and endure within reach of home before reaching farther. It may depend on whether we can become the kind of species that treats maintenance as noble, that designs for repair, that keeps redundancy boring, that respects the physics of air, water, heat, and time. And if we do that, the most important frontier may not be distance at all. It may be permanence. The ability to keep a light on, through long nights, on a world that does not care whether we are there. And perhaps the strangest part of all is this. The first human city beyond Earth may arrive not when we finally reach the impossible, but when the familiar moon quietly becomes home. And when the moon becomes home, even for a small number of people, it also becomes something else, a school. Not a classroom with lectures, but a place where physics gives frequent exams, and where the grading is immediate and sometimes unsettlingly quiet. On Earth, if a pump fails, you open a window, you call a technician, you breathe while you wait. On the Moon, every failure feels more absolute because the environment offers no forgiveness. And still, the Moon is close enough to be practical. Close enough that spare parts can be launched without waiting for seasons. Close enough that design teams can respond while memories are fresh. Close enough that the culture of the settlement can stay connected to the culture of Earth, long enough to develop its own careful habits, without being thrown into total isolation too soon. That is a strange balance, danger, and recoverability. And it may be the most valuable thing the Moon can offer. Because becoming multi-world is not only a transportation problem, it is a discipline problem. It is the slow learning of how to live with closed loops, how to treat air like a resource you measure, not a background you ignore, how to treat water like a system, not a convenience, how to design homes where repair is not an emergency, but a daily ritual. In that sense, a lunar city is not merely a replacement for a Martian dream. It is a rehearsal for futures that go deeper than Mars and quieter than heroism. A rehearsal for the kind of civilization that can keep its promises to itself, even when no one is watching, even when the sky is black and silent for days at a time. And in this rehearsal, there is another presence, steady, tireless, and increasingly central. Machines, not as decorations, not as assistants in the background, but as the majority of the workforce. Because the human body is precious in space. Every hour of human attention is expensive. Every risky excursion outside is a negotiation with probability, and every task done by a person is a task that had to justify the oxygen, the food, the shielding, the training that brought that person there. So the future of work on the Moon and on Mars leans toward robotics and toward autonomy. You can already see the early outline of that future in how robotic explorers behave on Mars today. The Perseverance rover, for instance, has demonstrated driving modes where it can do more of the thinking on board. It does terrain analysis with its cameras. It searches for hazards like sharp rocks, loose slopes, wheel traps, and it can generate its own machine-chosen waypoints, small decisions stacked into a path. Because waiting for humans to approve every meter of progress is not realistic on a planet that is light minutes away. This is not consciousness. It is not curiosity. It is a narrow kind of competence. And that is exactly what makes it powerful. Because distance creates delay, and delay creates a need for machines that can handle the immediate present. The kind of present where a wheel is slipping right now, where a battery is draining right now, where a dust plume is building right now, where a thermal limit is being approached right now, and no human voice can arrive in time to prevent the mistake. Even around the Moon, where communication is fast, there will still be moments of disconnection. A rover behind a ridge, a construction site in shadow, a network saturated by competing demands, a lander in a brief, critical phase where it cannot afford outside confusion. Autonomy matters, because complexity happens faster than committees. And if you imagine building a city, not a visit, not a camp, but an actual city, you can feel how quickly the task becomes too large for constant human supervision. Autonomous systems can inspect terrain for stability, reading the surface for subtle signs of collapse, finding safe places for landing pads and heavy structures. They can move cargo, again and again, without requiring a human to drive every trip. They can plan routes that minimize dust, avoid steep slopes, and reduce wear on wheels and joints, so that machines last longer in an abrasive environment. They can monitor risk continuously, not just the obvious risks, but the ones that arrive like slow arithmetic. A small leak that is too small to hear, but not too small to matter. A filter that is gradually clogging. A motor drawing slightly more current each week. A vibration pattern that suggests something is loosening. A CO2 scrubber trending in the wrong direction. Quietly, patiently. Until one day, it is no longer a trend. On the Moon, this becomes directly connected to construction. If regolith is used for shielding, then regolith must be excavated, transported, piled, compacted, and these are perfect jobs for machines that do not need oxygen, that do not care about boredom, that can work slowly and precisely for long stretches. If habitats begin as converted vehicles, then those vehicles must be stabilized in place, surrounded by berms, and perhaps gradually buried under meters of lunar soil, not as an aesthetic choice, but as a practical response to radiation and micrometeoroids. If the South Pole is the main site with water ice in permanently shadowed regions nearby, then machines will likely do the first harvesting, the first hauling, the first processing, because the cold there is not merely uncomfortable, it can be mechanically brutal. And power, always power. Solar arrays placed along ridges, cables running across uneven ground, batteries housed in insulated vaults, switching systems that must keep working in harsh thermal cycles. These are infrastructure projects, and infrastructure is where the romance of exploration becomes the routine of civilization. This is why smarter machines matter for both the Moon and Mars, not because humans are being replaced, but because humans should be protected from spending their limited time on tasks that machines can do reliably. A human crew should be focused on judgment, on science, on decisions that involve ethics, priorities, long-term planning, and the subtle understanding that comes from being alive. Machines can take the steady work, the continuous inspection, the hauling, the repeated assembly steps, the night shift that never ends. So the path to a lunar city may depend as much on machine competence as on rocket capacity. A reusable launch system changes the entry cost, but autonomy changes the staying cost. It changes whether the settlement is a sequence of fragile missions or a stable system with momentum. And that leads to a deeper pattern, one that may quietly shape the future of human expansion more than any single destination. Civilizations grow when they shorten the distance to failure. That phrase can sound pessimistic, but it is actually a kind of optimism disciplined by experience. If the penalty for a mistake is total collapse, then people become conservative, progress slows, and risk becomes taboo. But if the penalty is survivable, if mistakes become data, then learning accelerates. The moon is close. That closeness means rescue is at least thinkable. It means resupply is practical. It means rotations of crews can happen more frequently. It means new designs can be tested and revised without waiting years. So a moon-first approach is not only about resources or politics, it is about learning speed. A lunar base that can be expanded into a city teaches the boring necessities: how to store spares, how to standardize connectors, how to document procedures so clearly that no one needs to guess, how to build systems that can be repaired by someone who did not invent them. These are not glamorous skills. They are the skills that keep people alive. And if you allow yourself one quiet image, just an outline, you can sense what it might feel like to live inside that growing structure. You might wake in a habitat lit by artificial dawn, because outside, the sun's schedule is not yours. You might walk down a short corridor where the walls are thick, not to feel safe in a psychological way, but to reduce radiation dose in a statistical way. You might hear fans, pumps, the small constant evidence that life support is working. And then, perhaps during a planned excursion or through a carefully shielded viewing port, you see Earth, not as a distant goal, but as an object in the sky, a bright and fragile disk. You might feel a kind of continuity, the realization that home is still there, still turning, still full of weather and oceans and people who will never know your routines. And you might also feel something slightly eerie, not fear, just the calm recognition that the system you live in is not the Earth. It is a deliberate environment, a place where the difference between life and death is measured in valves, in seals, in power margins, in whether the next shipment arrives on time, in whether the robots kept working through the night. And yet, if it becomes stable, if it becomes ordinary, then the moon changes forever in the human mind. It stops being only a symbol and becomes a place with addresses, with supply rooms, with schedules, with rules about dust, with arguments that sound exactly like arguments on Earth, just held in lower gravity. And this is how the first city beyond Earth may truly begin. Not with a single leap that rewrites everything overnight, but with accumulation, with fast iteration supported by reusability, with habitat conversion instead of waste, with South Pole resources treated as a careful industrial project, with regolith shielding because the moon offers little else, with economic sustainability measured as continuity, not spectacle, and with autonomy, everywhere, quietly extending human capability. Over time, the landing pad becomes a small network of pads, the first habitat becomes a cluster. The first cluster becomes a neighborhood of connected volumes. The power system gains redundancy. The warehouses grow. The procedures become calm and standardized. And something that once sounded like science fiction begins to look like municipal planning. Then the central question returns, not as a slogan, but as a patient inquiry. Does humanity's first true off-world civilization begin on the moon, not as a temporary outpost, but as a place where lives are fully lived? The answer will not come from wishing, or from perfect speeches, or from a single machine that solves everything. It will come from whether humans can learn to build systems that endure, and whether we can share the work with machines that are competent enough to carry the weight of routine without carrying the weight of meaning. Because perhaps the most important frontier is not distance, but permanence, the ability to keep a light on through long lunar nights in a shelter built by repeated nearby steps. And perhaps the strangest part of all is this: the first human city beyond Earth may arrive not when we finally reach the impossible, but when the familiar moon quietly becomes home.